All right, suppose that we have a graph G, and we're going to let A and B be two subsets of vertices with the property that their union consists of all vertices and their intersection is empty. So in other words, you've taken your graph and you split the vertex set into two parts, A and B. Then we're going to call this splitting into two parts a bipartition if it has the following property. The induced subgraph on A and the induced subgraph on B have no edges. In other words, every edge in the graph has to have one endpoint in A and one endpoint in B. All the edges have to run across the split. So if a graph has a bipartition, we will refer to that graph as being bipartite. So one example of a bipartite graph is called the complete bipartite graph on m vertices and n vertices. So this is where you have each of your sets in your bipartition. One set has size m, one set has size n, and we put all possible edges while keeping the requirement that this graph be bipartite. So for example, if we look at the graph we had seen in the previous video and we look at its complement, we see that the complement is bipartite. If I separate the top three vertices into one group called A and the bottom vertices in a group called B, I see every edge runs from a vertex in A to a vertex in B. Note that being bipartite does not mean we're requiring certain edges to exist. So for instance, there's no problem that there's no edge between this red vertex and this yellow vertex. The issue is that we're guaranteeing that there are no edges between two red vertices and no edges between two yellow vertices. So for an example of a graph that's not bipartite, we'd have to look back at the original graph we started with. So if I decide to put color one vertex red to put it in set A, then I see both of its neighbors would have to be in yellow because every edge has to go from a red vertex to a yellow vertex. But I immediately see a problem because there's an edge between these two yellow vertices. So we see this graph cannot be made bipartite. Mainly because no matter what bipartition or attempt at a bipartition you make, this vertex has to be in one of the two parts, and its two neighbors would be forced to be in the other part and yet also still be adjacent. Now down below I have drawings of complete bipartite graphs. So as you can see, in a complete bipartite graph, you can put all the vertices in A on top and all the vertices in B on bottom, and then you connect all possible edges. You can extend the definition of bipartite to being k-partite. So a graph is k-partite if you can separate the vertices into k sets. So here is k equals 3. So we're going to call them A, B, C, although for the general definition, we have to use V sub 1 through V sub k. And of course, to be a partition of the vertex set means that each of these subsets' intersection is empty, pairwise the empty set, and yet every vertex appears in at least one of these sets. And so the rule is the same as before. You're allowed to have edges between vertices of different parts, and you're not allowed to have edges between two vertices of the same part, in the same part. And yes, this does mean it's possible to define a complete k-partite graph where you're specifying the size of each of the vertex sets, and that would mean that you don't not have any edges within the part, but anytime you have two vertices in a different part, you would have to have an edge. So for instance, if I wanted to draw k1, 2, 3, I'd have a part size of size 1, a part set of size 2, and the remaining part set has size 3, and then the rule is that I have to connect vertices from different parts. And then that means I still need to make this bipartite graph down here. So as you can tell, complete k-partite graphs get very hard to draw very quickly. So now we have to discuss some ways to build new graphs from old graphs. There's exactly 3 such constructions we're going to cover. Given two graphs G and H, in general we're going to define their union to be the graph whose vertex set consists of the union of the two vertex sets. And, while not listed, the edges are the union to the edges. The most common case that tends to pop up in this course is called the sum, which is the case where the two vertex sets are entirely disjoint. So for instance, I have these two graphs here. We see they don't have any vertices in common, so by definition, their sum is just taking the union. So I'm just grouping both vertex sets together, keeping all the edges I had in both graphs separately, and then adding nothing new. On the other hand, the join is taken by taking the sum of two graphs, and then for every vertex in one graph to every vertex in the other graph, I add an edge for all possible ways to do this. And so one way I tend to think about this is you're taking the sum of two graphs, and then you're adding in all the edges for the corresponding complete bipartite graph with the vertices in G as one part set and the vertices in H as another part set. But here I should be careful and point out I'm talking about union, so we are still keeping these other edges. Finally, I'm going to introduce the adjacency matrix, which will pop up later in the course. Given any graph G with vertices V1 through Vn, and here I am putting subscripts on the vertices for a reason, you can construct a matrix. It's called the adjacency matrix. It is a square matrix where the number of rows and columns correspond to the number of vertices. And the rule is that you put in the number 1 in an entry if the corresponding vertices are adjacent, and a 0 if they're not. So for instance, if I take this graph here, where I've chosen to label the vertices 1, 2, 3, and 4, then that tells me that the first vertex corresponds to the first column and first row. The second vertex is going to correspond to the second column and second row. The third vertex is going to correspond to the third column and third row. And finally, the fourth vertex is going to be the last. And so since there's an edge between 1 and 2, I should see a 1 in the first row, second column, and also in the second row, first column. And so you see for each of these edges, you can find exactly 2 entries in the matrix that are both 1. So another example is 1, 3, first row, third column, and third row, first column. On the other hand, since there is no edge between 1 and 4, I should see in the first row, fourth column that there's a 0, and likewise in the fourth row, first column, there should be a 0. Note that this means that the matrix is going to be symmetric, which means that when you take the transpose, you get the original matrix back. The reason why that's true is because if vertex I is adjacent to vertex J, then vertex J has to be adjacent to vertex I as well.